A system is optimized for speed, but its wait times get longer. Now that outcome defies all intuition. But it isn't an accident. It's the product of a hidden structure, an invisible logic that turns the very pursuit of efficiency into total gridlock.
The logic seems so direct, right? If you want to shorten a line, you just have to speed up the service. Whether you're at a checkout counter, a support desk, or managing a data network, the goal is always to increase the speed of processing. It's the most rational response to any delay.
And yet, this is what we see happen. Projects designed to increase throughput, to make things faster, end up creating even longer lines. The system, now technically faster than ever, starts to generate delays far worse than the ones it was built to solve.
This outcome isn't just bad luck. It isn't a coincidence. It's the logical, predictable result of an underlying structure, a set of rules that governs the flow of pretty much anything through any system. You can't see this structure, but its effects are profound. So to see it, we need to strip things way down. So, let's consider a simple physical system. A funnel. You drop marbles into the wide opening and they exit through the narrow neck. Its behavior is simple, clear, and governed by the laws of physics.
You know, every system, no matter how complex it seems, really shares this same basic structure. You have things arriving, they get processed, and then they depart. The marbles going into the funnel, those are the arrivals. The narrow neck where they have to squeeze through, that's the processing stage. And the marbles coming out the bottom, well, those are the departures.
And I want to be clear, this isn't just some abstract model. This is the call you make to customer service. It's the cars flowing down a highway. It's the data packets moving across the internet. Each one is a system of arrivals, processing, and departures. Okay, so what's the goal here? For any manager of a system like this, the objective is to increase the rate of flow. More calls handled per hour, more cars passing a single point, more data delivered per second. The whole point is to move more items through the system faster.
So, to get more flow, you increase the rate of input. You pour in more marbles. And at first, it works. The rate of departures increases. But then, pretty soon, a small queue starts to form at that point of constraint. The system is still working, but you're seeing the very first signs of strain.
This point of constraint, well, it has a name. It's the bottleneck. In engineering, in manufacturing, in networking, it's the one single part of the process that sets the maximum speed for the entire chain. You know, you could optimize everything else, but it's completely useless until you address the bottleneck.
And when you look at the data, you see this really alarming, nonlinear relationship. As a system's busyness, its utilization, climbs from, say, 70% to 80%, the wait time goes up a little bit. But then past a certain point, it just explodes. A tiny increase in how busy the system is creates this massive, disproportionate jump in how long you have to wait.
What's happening here is that as the system gets closer and closer to its maximum capacity, it loses its ability to absorb randomness, the normal, natural variations in arrival times or processing times. Things that it used to handle easily now cause huge delays. The system becomes incredibly brittle.
So, in response to this growing queue, another rational decision gets made. If you can't easily widen the bottleneck itself, you modify the system to accept more arrivals. You widen the top of the funnel. You increase the input capacity, even though that central point of constraint hasn't changed at all.
The result is catastrophic. The marbles now enter the funnel so fast that they jam together, forming a stable arch right over the bottleneck, which prevents anything from getting through. Flow doesn't just slow down, it stops completely. The attempt to manage the queue has created total gridlock.
And this isn't just an analogy. This is a real-world outcome. You hear about it all the time. A company invests in a brand new system to boost efficiency, only to find that its average response time has tripled. The rational pursuit of making one part better has produced a complete system-wide failure. So to really understand why, we have to look at the formal properties of the system itself.
So the formal term for a system's busyness is capacity utilization. It's simply the ratio of what the system is actually putting out versus its maximum possible output.
Think of it this way. When a system is operating at low utilization, it has slack. It has buffer. It could absorb unexpected surges or delays. But a system running at high utilization, it's brittle. It has no buffer at all. Any tiny disruption creates a shockwave of delays, and you get these huge, volatile queues. The drive for 100% efficiency actually creates fragility.
The mechanism behind this isn't a matter of management style or philosophy. It's actually a fundamental mathematical relationship. It starts with the total number of items that are inside a system at any given moment.
And that number is directly tied to the rate at which new items are entering the system. I mean, it makes sense. The faster things arrive, the more things are likely to be inside at any one time.
And it's also connected to how long each of those items actually spends in the system, from the moment it arrives to the moment it leaves. If items take longer to get through, the total number inside is naturally going to go up. These three things aren't just related, they're locked together.
This relationship has a name. It's called Little's Law. It states that L, the average number of items in a system, is equal to lambda, the average arrival rate, multiplied by W, the average time an item spends in that system. It's a simple, elegant equation that governs the flow of any stable system.
And this is the most important part to get. Little's Law is not a helpful suggestion. It's not a best practice. It is a mathematical certainty. Just like the law of gravity, you cannot violate it. You can only operate within its constraints. Any attempt to change one of those variables without accounting for the others is doomed to fail.
And this reveals the whole terrifying path to gridlock. It starts with a very rational desire to optimize a local piece. You see what looks like waste, idle time, buffer capacity, and you remove it. Utilization is pushed higher and higher toward 100%. The system then becomes fragile, completely unable to absorb normal, everyday variation. And the result is a total collapse from one tiny random event, a massive traffic jam from a single car braking, a network outage from a minor burst of data.
And this brings us to the final and most unsettling realization of all. The system that created that massive queue, it wasn't broken, it wasn't failing to do its job, it was perfectly executing the logic it was given. The pursuit of maximum local efficiency, when you apply it to a system governed by Little's Law, makes gridlock not just possible, but structurally inevitable. The question then isn't how we make systems faster, it's how we design them so they don't trap us inside their own logic.